All right. So as I introduced myself at the beginning of the session, I'm Brock Hedegaard. I'm with the University of Minnesota Duluth. I'll be talking about load rating of deteriorated concrete slab span bridges. Now, this project was supported by the Minnesota Department of Transportation, and I have to thank my collaborators with this. So Kendall Hill, who's now with MnDOT, was the master's student who did the vast bulk of the work on this project, and then Ben Diamond was actually the PI, he's now with Northern Arizona University, and we were also collaborating with Lauren Linderman at the University of Minnesota Twin Cities campus. So to dive right in, let's talk about the motivation for this project. So there's a set of slab span bridges up in northern Minneapolis right here, so in Brooklyn Center right here, that MnDOT was concerned about that they were load rating quite poorly. So there are 3 slab span bridges right here. And the reason that they specifically wanted to look at these is this is the main thoroughfare route if you're trying to go east to west through the cities there. So if you're coming from, say, Chicago or Milwaukee, you're coming in on 94, and then you're going out on 94 out to the western part of the state, and then also North Dakota, Montana. That's like the only interstate that goes through those states there. So largely we wanted truck traffic going through here, but these bridges rated so poorly that if we had oversized overweight vehicles such as this turbine blade, they're not allowed to take this particular route. So they had to take a 15-mile detour down the south of the city. It doesn't look that long, but it is quite a major cost that MnDOT was worried about. And so specifically looking into these bridges to see how they rated and how they were performing. The benefit of this also is that the work could extend to other slab span bridges around the state using this as sort of a test state study. So our research approach, we were doing 3 different techniques for this. We started off with diagnostic load testing, so conducting diagnostic load tests on 2 of these 3 bridges to observe load distribution and the performance of those bridges. Then we constructed some detailed FEM models, so this was 3-dimensional nonlinear finite element models validated with the field data to try to capture that load distribution, considering the damage state of these bridges. And I'll show you some of the pictures of that damage in just a little bit. And finally, the last step was to propose some simplified FEM models to expand to other bridges about the state. MnDOT was really looking for something that they could apply at minimal cost and minimal computations. And so we had proposed a simplified plate model to get some efficient results for that. So looking at these examined bridges, so again, they're slab span bridges, so there are no girders supporting these things. The deck or the slab is your structural system. So here's just a view from the side right here. There are some deflection joints here that's going to come into play when we get into the modeling. Top surface actually looks fine. These were overlaid not too long ago, but if you go underneath the bridge, there's a lot of delamination, a lot of spalling. Most of these are going longitudinally along the length of the bridge at multiple locations under it. And all the bridges were in a very poor condition, which is one of the reasons that they were rating quite poorly. So a little bit more detail on the 2 examined bridges. We looked at 2 of the bridges that had different aspect ratios. So 2 of the 3 bridges actually are similar to this bridge 2 here with the 74-foot wide bridge. And then we also looked at the more narrow 44-foot wide bridge as well. Span lengths are about 24 feet, and so span lengths are similar for each case. In terms of the reinforcement, we have a typical just double layer of reinforcement, X and Y directions there on top and bottom of that slab. So going into the bridge testing, we used 2 standard MnDOT dump trucks right here loaded with sand. Each of these trucks weighed about 50 kips, so we did a variety of load testing where we had single truck loading, double truck loading back to back right here, and then also a variety of side to side loading combinations. Quick look at the instrumentation. Most of the instrumentation that we used was going to be these strain gauges with the extensions on them. So it has effectively, I'm trying to remember if this was a 18-inch gauge length. I think that sounds about right. To try to make sure that we're getting sort of an average strain over a decent length, and then placing these all the way along the width of the bridge. And we were augmenting that with a variety of LVDT sensors here on tripods, also across the width, to try to get that distribution, and a handful of tilt meter sensors right here. So another view of our instrumentation scheme for the first bridge, bridge 1 here, we would have strain gauges across the width, and then we had a handful of LVDT displacement sensors at that location, but when most of our LVDTs in this case were on the final span here, just so that we could look at both spans and possibly compare the ease of application and ease of use of these two different types of sensors. MnDOT was kind of interested in that. We were rather interested in it too, seeing what is actually going to be a little bit easier in terms of monitoring these things. Looking next at bridge 2, here we just looked at one single span, concentrating all our instrumentation on this. This was mainly just a cost-saving measure. We weren't originally planning on load testing this bridge, but it turned out they were going to have a closure on the interstate anyway, and so we were like, yes, thank you, because that's not something that you get very often. So then we went in there, we slapped a bunch of sensors on a single span and tested it as quickly as we could. So that was the goal with that one. Again, LVDTs and strain gauges across the width, primarily measuring, we're primarily looking at flexural load distribution, not so much shear, so we don't have sensors also at towards the support here. So just a few more pictures from the truck tests, just seeing a couple of those different truck configurations. Again, we had a lot of single truck configurations, double truck back-to-back, and side-to-side. One thing to note with the side-to-side configurations, we were trying to look into the multi-lane distribution factors from AASHTO. When you have multiple loaded lanes, that's not always particularly of interest for overweight, oversized vehicles, because usually they're going to be going along the bridge on their own with an escort. But it was something interesting that we wanted to look at anyway. One thing that we didn't consider until after the load tests were done, of course, was that we probably placed these trucks a little bit too closer to find that distribution factor, which AASHTO is probably going to be assuming if you're placing your trucks in lanes that there's at least probably a 4-foot gap between those, and we had placed them as close as possible. So we'll keep that note in mind when we look at some distribution factors for multi-lane cases, that our truck tests are going to underestimate how much that load would tend to spread if you have vehicles in two separate lanes, for example. All right, so some information on our detailed FEM model before we get into the results, and I'll present all the results for the truck tests, the detailed FEM, and the simplified FEM all together here. With the detailed FEM, it is a three-dimensional FEM model created in ANSYS. We did explicitly model damaged regions along the length of the bridge, which effectively we're modeling with just a reduced stiffness area in there, and the widths are shown here. Some typical boundary conditions at piers and abutments. I don't think we need to spend too much time on that. You'll notice it's maybe kind of hard to see in the presentation. Ooh, I got too close to the mic. We did explicitly model gaps where we have displacement joints in that barrier, because the barrier does make a difference in terms of how that load is carried. So just looking at a couple quick preliminary results that we got from this, whether or not we included the barrier or not. Solid lines are including a barrier. Dotted lines are excluding the barrier. The barrier does a lot, especially for slab spans. Barriers are effectively your girders in some sense that you only have on the edges. So it makes a very big difference for slab span distribution. We also looked at different levels of cracking. So when we say elastic, that means we had no damage regions placed in there. And then just a couple like preliminary cases where we looked at 2-inch damage regions or 24-inch damage regions throughout the bridge. In the remaining results that I'll present, the damage regions were as surveyed in the field, shown right here. But we just kind of wanted to look at how much difference modeling that damage made. And it does make quite a bit of difference in terms of getting peak displacements, for example, right here, whether or not you have those large damage regions. This is the same idea, but just looking at midspan, with the load in the middle of the bridge here. Obviously, the barriers don't matter quite so much, but level of damage matters probably a little bit more when you have the load in the center of the structure. Next, to talk quick about our simplified plate model. So despite the picture here, this is just an extruded, graphical visualization of the cross sections here. So we did have cross sections for our barriers there, which are rather simplified from the actual barrier distribution. what we did is we cut it off at the height of that deflection joint so that we could just model a simple rectangular beam along the edges, because MnDOT said that was easier. So hey, why not? And to capture damage levels, we used orthotropic stiffness for the two different directions, longitudinal and transverse, of the bridge, depending on the damage state of the bridge. So a lot of these bridges had very little damage, say transverse cracks along the width. So stiffness in that direction would be pretty close to I gross. And then in the opposite transverse direction, you would have a much lower stiffness because we had rather extreme levels of damage in there. So a lot of times when we model this, we would model it with a, for example, just a simple uncracked calculation. And these are numbers that they can easily calculate. So they could do this even without possibly a field survey, though in general we'd encourage that. Anyway, so just doing a quick comparison of our detailed and simplified FEM versus some of the truck test data that we had looked at. If we place the trucks near the barrier, so the red dots down here are the truck position, x-axis is the width along the length, or the width across the bridge, and then either strain or displacement on my y-axis. We can see that the models for strain actually work out very well. There are obviously some differences in the data here, especially where you have localized, it says location of crack, but that's really a reduced stiffness zone in our detailed FEM, which kind of throws everything off. In terms of the displacement, overall, our simplified model had just generally less displacement. It spread out the load a bit differently, but in terms of the prediction curve, interestingly, they were just sort of offset from each other. MnDOT thought this was acceptable. They weren't quite interested in the total amount of displacement, but rather using this as a tool to estimate an equivalent width. And so we were not too concerned about the fact that we were under-predicting the displacement by about 20% with our simplified model in this particular case. Moving on, similar results for load placed near the center line. So again, our load is going to be in the center of the bridges here. And displacement being under-predicted by a simplified model, but as we'll see later, the predictions of equivalent width for doing a load distribution calculation were very, very similar. And a variety of simplified FEM validation plots. I won't discuss these in too much detail. It varied depending on where you place that truck, how well this model worked, and that's probably likely because the damage, in our case, we assumed it was just an eye crack across a transverse width. And if you put load directly above one of those places that has extensive spalling or lots of delamination, you're probably going to get different kinds of results. So overall, we thought it was at least an acceptable method. So in terms of our equivalent width calculation, what exactly would MnDOT want to do with these results? So the equivalent width, of course, is going to tell us what width of bridge, or bridge deck in this case, is going to carry our traffic loading. And so we have the typical AASHTO equations right here. And what we did from our calculations is we would look at the white area in between here would be the width of the truck itself. And then we would try to find the red area here that matched the blue area under the curves for our load distribution. So we could do this both for displacement data and for strain data, and to try to estimate an equivalent width both from our models and from the load test data. So what's the result of this? Let me put that yellow line showing that this is unity. So this is the observed equivalent width divided by the AASHTO equation equivalent width. And so in general, we're seeing better load distribution overall of these bridges than would be suggested by AASHTO. MnDOT's quite excited to hear that because we can pump out a little bit more load capacity out of these things. That held even for the field measurements, except for these black curves. The black curves are the multi-lane factor. And again, this is likely because we had placed those trucks very, very close together. So this is for two trucks that are almost touching, whereas the AASHTO multi-lane factor is approximating roughly 4 feet between those vehicles. So how does this affect our load rating? For both bridges, it does improve the load rating, and this is not accounting for if you want to do in situ testing. For example, we did some testing of the concrete and the steel properties of some of these bridges with some cores, and the strength was much, much higher than we were expecting. Bridge deck was surprisingly about 9 KSI. It's very old concrete, so it could have aged quite a bit. And then even though per design it was 60 KSI steel, we measured about 80 KSI yield on that. So This is not accounting for any material properties with destructive tests if you want to account for that. So this is literally, if you were just going to use a model and assume design properties, you can get roughly 50 or 30% increase in load rating just by better understanding of that load distribution of the damaged structure. So some quick conclusions and guidance that we gave to MnDOT. So for our field testing equivalent width, we did find that our equivalent width was similar using either strain or displacement transducers, which was nice to know. So whether or not we'd want to place one type of instrumentation versus the other might depend on site characteristics. We did achieve some rating improvements just using a equivalent width diagnostic test or using these models. And the simplified model with orthotropic stiffness did give us what we needed, at least. And so one thing to think about whenever you're modeling is what exactly is this model going to be used for? So even though perhaps it's not going to give us a very accurate estimate of the deflection under the load, it can give you a reasonably accurate estimation of that live load distribution. So with that, acknowledge a lot of the students that helped out with this project, and our lab staff, et cetera, and I'll open it up for questions. So thank you very much.